All right, welcome back, and it's time to move on with the show with another really great talk. Our next presenter, you might know him as one of the co-hosts of the Point-Free video series, which is an excellent video series about functional programming in Swift. He's also a true functional programming enthusiast, and he's going to talk a little bit about how protocol-oriented programming, which is very hyped up in Swift, might not always be the right solution. And instead, there might be some other venues that we can explore, specifically protocol witnesses, which I think is going to be fun to hear about. So, give a very, very warm welcome to Brandon Williams.
Thanks. Hi. Hi. Thanks for the intro and thanks for coming. Today we'll be talking about alternatives to protocols as a means of abstracting code and writing generic code. The talk will be split up into two parts, like the first part dedicated to the theory of protocol witnesses, whatever that is, and then an in-depth look at an example where I think the idea really shines. My name is Brandon. This is my contact info if you have any questions. I'm currently doing consulting for companies. I do talking about functional programming with companies, and I do this video series with my colleague, Steven Sellis. And everything I'm talking about today is joint work with my collaborators. So this is his contact info. You should feel free to also reach out to him. And also the entire site of Point-Free is built in Swift, server-side Swift, and it's completely open source, and we use these ideas in the code base. So if that interests you, you could go look at that. So on to the real meat of the talk, protocols. Protocols are great. I love them. You probably love them. Apple certainly loves them. I don't think there's been a single WWDC since Swift was announced that they haven't had some presentation dedicated to protocols. I'm sure everyone has seen the eponymous protocol-oriented programming talk and featuring the lovable Krusty. It's a good talk, and it had a lot of great ideas in it. So I think it's completely reasonable for us to walk away from those presentations thinking that protocols are a very powerful tool for abstraction. The more we use them, the more we will be able to write maximally generic code, very reusable code, and a lot of really great, powerful things will come out of it. However, that isn't entirely true if for no other reason than protocols have a lot of problems. Perhaps the gnarliest of all the problems is this one, which I'm sure everyone has seen at some point. The moment you use an associated type or self with a capital S in your protocol, it just behaves completely different than any other protocol. And you can't use it in a lot of ways you would want. You can't use it as the type of a variable. You can't have an array of those things, amongst other things. But this error won't be around forever. The Swift team is working on ways of getting around this problem, and they'll fix it someday, and this problem will, be gone. And in fact, they've even fixed a lot of protocol shortcomings relatively recently. It may be hard to remember, but it's only been 1 year that we've been able to write code like this. It was in Swift 4.1, which was 4 years after Swift was announced. And it's this line right here. This is conditional conformance, where you say a generic type conforms to a protocol when its generic is constrained, or also conforms to a protocol. So it took 4 years for us to get this, but we got it. But then there's things that protocols can't do that I'm not sure is really even on the horizon of being fixed. So here, we are trying to extend void to be equatable. That makes sense. Void only has one single value, and it's, of course, equal to itself. So we should be able to do this, but we can't. More generally, we should be able to extend a tuple of equatables to be equatable. Here, this is doing two things that are actually impossible, two things. One, you can't extend tuples, but also you can't introduce generics into an extension, because here, A and B, where are they coming from? They're kind of we're specifying generics to be used within the extension itself. We also can't extend functions to conform to protocols. So in this case, I'm trying to make functions from A to B to be equatable when A is case iterable and B is equatable. And this is totally possible to do. case iterable just says that you have finitely many values in your type, and you can just get them all and enumerate over them. But we can't do this. And this is a real limitation. You've probably run into it, especially if you've ever tried to test against something involving tuples. Because tuples are not equatable, you can't do something as simple as this. You'll get this area saying that tuple does not conform to equatable. So it's a real problem. But then protocols have another limitation, in which types are only allowed to conform to a protocol in one single way. And that is the definitive canonical way that that type can conform. So here we have a tree type, like a binary tree, and we want to make it iterable by conforming it to sequence, and that would unlock all types of interesting generic algorithms that the standard library gives us. But what do we do? Do we iterate over it depth first, in order, pre-order, or post-order? Or do we do breadth first? Like, no one of these is more important than the other one. They're all important. But due to the limitations of protocols, we have to choose one, and that will be the one way of iterating over this tree. And then there's this defect of protocols, which I just have a very simplified version of it, and we'll run into this in a moment in a more real use case. But if you have two protocols, you cannot, after the fact, extend one protocol to conform to another protocol. Even if you provide all the requirements right there, you can't do this. And I don't know of a legitimate reason why this is not possible. I think it's probably just, it hasn't been proposed and designed yet, so maybe someday we'll get this, but this is another thing that protocols cannot do. So if protocols are the primary tool for abstraction in Swift, and Apple pushes it very hard, but there's significant problems with it, what are we supposed to do? And it turns out there is a very simple process in which you can convert pretty much any protocol into just a very simple data type. And when you do that, most of these problems go away. And the ones that don't go away, it starts to become very clear why they're problems. Like, you kind of get at the root idea of what's going on. But more importantly, in my opinion, is when you do this process, you'll start to uncover like transformations that are very surprising and very useful that are just completely hidden from you when you're living in the protocol world. So you'll actually recover something that protocols can't do. And that's what I find most exciting. So let's just describe the process of deprotocolization and see what it gives us. We're going to start with the protocol, a very simple one, and convert it to a very plain, run-of-the-mill data type. And in doing so, we'll get some interesting things. So this is the protocol. It's called combinable, and it just expresses the idea of a type that can combine itself with another value of that type to then produce a third value of that type. There are a lot of types that conform to this protocol. Strings are combinable, because you can just concat them. Arrays are combinable in pretty much the exact same way, because you can concat them. But already we're kind of running into something kind of strange, because array is a very specific type that can be, a very specific collection that can be concatenated. There's a far more general type called range replaceable collection that is a subtype of collection that adds the feature of being able to concatenate. So you may be tempted to do something like this. You would want all range replaceable collections to be combinable. But of course you can't do this because range replaceable collection is a protocol, and you cannot extend protocols to conform to other protocols. So already we're missing out on a whole world of like potential generic code reuse, because we are now tasked with defining combinable instances on every range replaceable collection we know about, but then all the ones we don't know about, we can never provide those conformances. We leave it to those people who created those range replaceable collections to pick up where we left off. And that's kind of a bummer. This could be very generic if we could do this. All numeric types are also combinable. Here we just made int and double combinable by using addition. But also Swift ships with like a dozen numeric types. So all of those are combinable, and we'd have to implement conformances for all of them. But really, we'd like to do this, right? We'd like to just say, if you're numeric, then you should also be combinable, because we can just add, but we can't do this. And that's not even the worst part for numeric types, because they have another conformance. It's not just one conformance. We would like to say that numeric types are combinable in two equally valid, mutually exclusive ways where we use multiplication instead of addition. But you can't do this because a type can only conform one single time. Okay. So, and then also we would like tuples to be combinable in the case that each of its components is combinable, where you would just combine in each of the components, like this. And we would also like that functions into combinables are also combinable, where all you do is take two functions and combine them by mapping into B and then combining there. But we can't do any of this. All right, but all those problems aside, once you have your protocols, you want to start writing generic algorithms on them, because this is where code reuse happens. Every algorithm you write on a protocol is code that you are getting for free for every single conformance of the protocol. So probably everyone is familiar with the reduce function. It allows you to start with an initial value and then combine values from an array into it using some kind of combine function. And so we can make this a little bit nicer by saying that collections whose element is combinable, well, in order to reduce those collections, we can just leave off the combine function because the element knows how to combine with itself. And so it only takes the initial value, and we can just reduce, and underneath the hood, we'll use the combine that comes from the combinable. And that's how you'd use it. You just get to simplify the call site a little bit by forgetting about the combining. You're just like, reduce this array into 0, reduce this array into the empty string, or reduce this array into the empty array. So that was a very simple protocol, and we ran into all the protocol problems like very quickly. So in particular, we would have loved if we could make existing protocols conform to combinable. We would have loved if we could make tuples and functions conform to combinable. And we would have loved if we could have had multiple conformances to combinable. So let's deprotocolize and then see what that gives us. This is how you deprotocolize the combinable protocol. You replace the protocol with a struct. And we rename it from the able suffix to ing suffix. So combinable becomes combining. All right? And we introduce a generic because this generic represents the self, represents the type that is conforming to the protocol. So A is basically like self with a capital S in the protocol world. And then the requirement, this method combine with an other self to return a self, becomes just a simple function field, just a field, a let field. All right, and it takes two arguments because the first one is like the implicit self that you have in a method. Whenever you're a method, you always have access to self, lowercase s self, and that is of type uppercase s self, the type that is conforming. And so that first A is referencing that implicit self. Then the next argument is the self that is actually being passed to combine, and then you return A, which is returning self with a capital S. All right, so that was the deprotocolization of our combinable protocol. And how do you use it? Well, instead of conforming types to the protocol, you construct instances of the struct. So instead of conforming int to be combinable by doing addition, we construct a combining of integers using addition. And we give it a name sum. And instead of conforming string to combinable, we construct a combining of strings using plus, but string concatenation. And then to write generic algorithms, instead of constraining generics to conform to protocols, you pass in explicit, let me back up one second. And we call these little values, concat and sum, we call them witnesses of the protocol because they are the proof, the concrete data proof that you have a conformance to your protocol. And so then to write generic algorithms, instead of constraining your generics to a protocol, you pass in an explicit witness. You're not like, my element is of combinable. You're like, it can be combined because here's the proof, here's the witness to the combining requirements. And then underneath the hood, you just can use combining.combine like you would use it over in the protocol world. And then at the call site, you pass in the explicit witness to say, this is the way in which I want to reduce. But because these protocol witnesses are just values, you can construct as many of them as you want. So I've got a combining of integers as addition and a combining of integers as multiplication. And so I can reduce with the sum or reduce with the product. I get to come up with as many combining witnesses of 4 integers as I want. And there's no clash. I just have to decide at the moment I want to invoke my algorithm, I have to decide which witness I want to use. So protocol witnesses are solving that problem. But witnesses also solve the problem that prevented us from extending numeric to conform to combinable. So here, I have greatly generalized sum and product so that they do not work on just integers, but they work on any numeric type. So I extend combining, and I constrained its generic to the protocol that I want to work on, numeric. And now sum and product are computed variables that can be accessed for any numeric type. So immediately, I already get, just with those two, the ability to reduce with sum and product on integers, doubles, CG float, anything. Like if you created your own library of like vector math and matrix math or quaternions or whatever, you would just instantly get access to this because I have made this combining algorithm work for any numeric type. All right, so now it solved that problem. All right. This is also kind of nice that these two witnesses, sum and product, have now been kind of namespaced also within the combining type. They're not just floating around as like globals in the module namespace. They've like kind of been anchored a little bit, and that's why we have these dots here. So it's nice that we can still use type inference. We don't have to specify combining.sum, combining.prod. So even that's kind of nice. We can do the same with range replaceable. Here I've made combining work on any range replaceable. So that means this one implementation works for strings and arrays. I don't need 2 separate concats, one for strings, one for arrays. It also would work on array slices or anything that's range replaceable. If you have your own library that has a range replaceable, your own custom range replaceable collection, it would work instantly. And then there's even more. So remember how I said that tuples cannot conform to protocols, but this is doing precisely that, but for witnesses and for the combining type. Because this says that if you give me a way of combining A's and a way of combining B's, I will give you back a way of combining A's and B's, where we just do component-wise combining the left and right-hand side. All right? And it may seem a little weird that I'm calling this function zip, because you're probably all familiar with zip on arrays. But I did this because zip on arrays is a special case of a far more general idea. Because in words, if you think about it, zip on arrays is a transformation of a tuple of arrays to an array of tuples. And this is saying this is a transformation of a tuple of combinings into a combining of tuples. And you can keep on going. You can do this for many different types. You could say a zip would be a transformation of a tuple of promises to a promise of tuples, or a tuple of parsers to a parser of tuples, or even a tuple of optionals to an optional tuple. That, like zip as a general idea, is able to do this transformation between generic containers and tuples. So that's why I've called it zip. It's also worth noting that this function is expressing the idea of conditional conformance, because it's saying if A and B are combining, then tuples of A and B are combining. So in the witness world, conditional conformance is nothing but a function that transforms witnesses to witnesses. That's all conditional conformance is, just a function. And then finally, it's worth noting that this code would have compiled in Swift 1. So in Swift 1, we would have been able to have some resemblance of conditional conformance. We would have had some resemblance of conforming tuples. Long before we had conditional conformance or any of these things, this code is perfectly valid Swift 1 code. So that's how simple this idea is. Okay. And the zip function is like packing a serious punch, because here we have an array of tuples, and we're going to reduce the first component of the tuple with sum and the second component with concatenating. And so in just one iteration of the array, we're doing both those operations on the components. And so this, I think it's packing a pretty serious punch. And then you can also, of course, do combining on functions now. If you give me a way of combining B's, I will give you back a way of combining functions into B's, where to combine two functions f and g, I return a whole new function such that f and g just gets applied to the input, and then we combine over there in the B world. So we're getting conformances, conditional conformances on functions now. So that is the basic theory, although I know there was a lot packed in there, but that's the basics of deprotocolizing. And there's a lot more to cover before you can really use this in the real world, because there's a lot more protocol features you need to figure out how to deprotocolize, like associated types and all types of stuff. But that's the basics, and rest assured all that can be done, but maybe it'd be better to look at an example where this idea just really shines. And it's in a library that I open sourced with my colleague Steven, and it's a snapshot testing library. It's been open source and in production for 2 years, or nearly 2 years, but we did the 1.0 last December. And the 1.0 is a completely different from the very first version we released. And that's because we started in the protocol-oriented style, and we were kind of constantly butting up against a lot of these problems, but it was working mostly fine. We're just rolling with it. And then finally we're like, enough is enough. Let's see what would happen if we just convert all these protocols to data types. And a lot of really amazing things happened. So first, what is snapshot testing? It's a form of unit testing in which you don't directly assert on, say, the output of some computation or some function, but instead you assert that the snapshot of some output is equal to to a snapshot that has been previously saved as an artifact on the disk. So instead of doing this, instead of importing XCTest and asserting that the output of some compute function is equal to 42, you do something like this. And when this is run, a snapshot is made of the output of compute 3, and then it looks up a file on disk that it can uniquely reference based off of the name of the test that we're running in, and then it compares those two things. And if they differ at all, the test will fail, you'll get a nice error message, and it can be pretty powerful. I think probably the most popular form of snapshot testing would be screenshot testing in the iOS community, in which your artifact is an actual image of some UI, and you save that UI or that artifact, that PNG, to disk, and then when this runs again, it'll load up the view controller, take a snapshot, and then compare pixel by pixel with the image and make sure everything is good. Here, this is some screen with a graph and stuff, but you can also screenshot test a variety of configurations for the screen. So what if you want to see what it looks like when it's in German, or when it's in Spanish, or when it's in French, or when it's in Japanese? You can do that kind of stuff, and it gets really powerful. But screenshot testing isn't the only form of snapshot testing. Snapshot testing is far more general, because you can snapshot any kind of value, not just views, into any kind of format, not just PNG images. So for example, you could snapshot a request, a URL request, and it would print out in a kind of a nicely formatted, as nice as you can do, format of all the different properties of that, because a request has a lot. It's got the URL, which includes a bunch of query parameters. It's got headers, and it's got a post body. And so you want to get a really good view of what that data looks like. And so here we have a post to a Stripe endpoint, and it's doing some URL encoding that can be tricky to get right in the query param. It's got a header for basic authorization, and it has a post body. And so if you were to write a unit test for this, a non-snapshotting unit test, you would be responsible for creating the URL request and filling in all these fields and then asserting against it. And that would take many lines to do, whereas this is one single line, assert snapshot, bam, you get this. And also, I think that's like so prohibitive to do all that work that you just wouldn't test maybe this part of your code. The code that in your API client or Stripe client or whatever prepares your URL request. You just maybe wouldn't test it because it's such a pain, and that can be not so great, especially in this wild west world of server-side Swift in which Linux Foundation is subtly different from Mac Foundation. We've had a lot of bugs working on Point Free that Snapshot Testing caught because of very subtle differences between the two foundations. Okay, so this gives you some very broad coverage with very little work. So let's talk about the protocol approach we took, see the problems, and then see the fix. So we wanted like a set of protocols such that types conform to those protocols, and then they would unlock like the generic algorithm of doing all the snapshotting and saving to disk and comparing and all that stuff. So we ended up with two protocols. There's a diffable protocol, which expresses the idea of types that can be diffed. There's a requirement that takes two values and diffs them. It returns an optional tuple, because if there is no difference, we'll return nil. It's like there was no difference. But if there is a difference, we'll return a string that is the error that would show in Xcode of what failed, and then an array of XC attachments, which are little artifacts that get saved into Xcode so you can go reference and see what went wrong. And you can return any number of these. All right? Then you need a way of serializing to data so that you can save it to disk, and a way of unserializing data so that you can resurrect an artifact from disk into memory. And then we'd have a snapshot protocol, a snapshotable protocol. And this expresses the idea of types that can be snapshot. They have an associated type because a type can be snapshot into a different format. So we need some format that is diffable. We'll need a path extension so we know how to save the file on disk, the .png, .txt, .something. And then we'll need the ability to turn ourselves into a snapshot in that diffable format so that we can then save it to disk, resurrect it from disk, and compare. And once we have the protocols, we can write our generic algorithm. We can write the assert snapshot helper that says, assert that we're matching some A, and this does all the work of loading the current artifact from disk, turning this A into a new snapshot, comparing those two things, failing the test if they differ, and so on. And we used this library in basically this form for a very long time, and it did perfectly fine. And even in this state, it was what I think is maybe like the best way of doing snapshot testing in the iOS community, but there were definitely problems. Of course, you can't have a type be snapshot in multiple ways. This is a completely valid thing. Even just a view, you would maybe want snapshot in multiple ways for different sizes, different configurations, size classes, and things like that. Also, when we're doing server-side Swift, we wanted to snapshot our web pages both as like the raw HTML like hierarchy and as an image of the page. And then there were a lot of types that we wanted to snapshot that we couldn't snapshot, as we'll see in a minute. So let's deprotocolize those protocols. Diffable becomes diffing, and it picks up a generic, which is the types that can be diffed. The static function from self-self to optional string XC attachment just becomes a field that's a function from value to string attachment. This has two arguments, and the static function has two arguments because it's static. There's no implicit self. We don't need to insert another implicit self value into this function. The computed property data, that's just a function from self to data, so from value to data. And then from is a function from data to self, or data to value. So that's deprotocolizing that. And then we can deprotocolize snapshotable, it becomes snapshotting, and we pick up a value generic. But then the associated type picks up a new generic, format. And because format is diffable, we pick up a diffing witness in our snapshotting witness. Path extension just becomes a field, a variable. And then snapshot is a function, that should be value to format because it's a computer property with an implicit self that then gets a format. And then our generic algorithm, instead of constraining to snapshotable, we take an explicit snapshotting witness. We say assert snapshot matching this value, but as some witness. All right, and we'll see an example of that in a moment. So the library comes with tons of snapshotting strategies, and it's really easy to create new ones, and you don't have to be shy about creating new ones because you're never going to step on the toes of other possible conformances. You should create as many conformances for UI view as you want or for URL request as you want. So let's take a tour of some of those strategies. Out of the box, there's a dump strategy where any data structure can just you can call Swift's dump function, which produces like this tree-like structure of a description of everything in the data structure. And this works on any data type, any with a capital A, that magical protocol that everything conforms to. You can snapshot any value. And you just get this, like this will give you very broad coverage with very little work. But if your type happens to be codable, then you get, of course, snapshots JSON. This is a strategy, well, the previous strategy wasn't possible in the protocol-oriented world. This one also, because we can't extend codable to be snapshotable, but we can do it here. Like before, we can snapshot requests in this like raw format where we kind of try to list out the headers and everything in a nice way. But you can also snapshot with a curl strategy so that you get an actual legitimate, valid curl description here that could be copy and pasted in a terminal. And then, of course, there's image snapshot strategies. You could snapshot a view, a plain UI view, but then you could also snapshot it as an image, but then you could also provide some custom traits so that you can test what does it look like in regular versus compact and things like that. But then you could also snapshot your view controller, and you could simulate an iPhone X in portrait. It'll set up all the sizes, all the size classes for you, and then you could also do in landscape. But you can also snapshot views in a textual format because there's this kind of magic debug function called recursive description that it's a private symbol, but you can call it in test code just fine. And it would print out a textual description of your view hierarchy. And this is very popular to do in the React community where you snapshot virtual DOM and get like a textual output and you track how refactorings would change that DOM. So you can just do this. But you can also snapshot controller hierarchies. This is the children controller hierarchy for a view controller. We have a tab bar controller. It's got 5 tabs that are all navigation controllers. And then inside the first tab, it has a UI page view controller. And so you could test that you're managing your children view controllers in the right way just by snapshotting their hierarchy. This is a third-party one. This is a project that provides a Swift wrapper around libharu, which is a C library for generating PDFs, and it's cross-platform. And the maintainer of this project created a custom PDF strategy so that he could snapshot his data structures into PDFs. So he gets very broad coverage of a very difficult format to test, because even the simplest of PDFs is actually just dozens, if not hundreds of lines of textual commands of how to do the whole thing. And so he gets a PDF sitting in his repo of like a real life artifact of what the PDFs look like as output from his library. So that's pretty cool. This is a very experimental one and not one that's public, but with Steve and we're working on a animation framework. And of course, you'd want to test an animation framework. And what better way to test an animation framework than to generate a GIF artifact of the animation? So you can just snapshot the canvas in which this animation is happening, and you can give it some parameters like how long do you want the animation to happen and how many frames per second, and it'll generate a GIF, and then you can do refactorings and see how that would change your animations. You could also just slow it down, and so the artifact that you commit to your repo is a very slowed down version. This is a animation. If you go to the Apple Arcade website, they've got like all these little animations with icons. So I just want to see if I could recreate it and write a snapshot test, and it was pretty easy to do. But then you could also have just very focused unit tests. So this is only testing what does the ease out animation curve look like in this animation framework. And so now this is just proof of what the animation curve looks like in this framework, just a simple dot going across the screen. But you don't only have to snapshot as a GIF, you could also snapshot as like an onion artifact. This is just a static PNG where I just take a whole bunch of frames, 20 frames, and then increase the opacity so you can see the evolution of the animation in just one single shot. And so I really think a lot of this was only possible because of the choice to get rid of the protocols and just use the concrete data types, because we have multiple snapshot strategies for a single type. And so I think we were getting a lot of benefits out of this. And that's very cool, but that's not even the end of it. There's other things that start happening when you go this like concrete data type route. You're able to derive all new strategies out of existing strategies. And this is the operation that does it. We'll step through it. It's called Pullback. I'll explain why in a moment. And it says that if you have a function that goes from new value to value, you can then transform your snapshotting on value to a snapshotting on new value. All right, and you should think of this operation kind of like map on arrays, which says that if you have a function from A to B, you can transform arrays of A's to arrays of B's. Here we're saying if you have a function from new value to value, you can transform snapshotting of values to snapshotting of new values. It goes in the opposite direction. The A and B have been flipped if you sit down and write it out, but they're very similar operations. And so to implement it, well, the diffing and path extension, that doesn't change at all. All that stuff carries over. The only thing that changes is the manner in which you snapshot, and all you do is take your transformation, apply it to the new value, and then snapshot that. All right? So assume you had a way of snapshotting UI images into UI images. All this does is serialize UI images to PNGs, deserialize PNGs back into UI images, and then given two UI images does a pixel by pixel diff on them. The implementation of this is kind of long, but it's somewhat straightforward, and Apple's APIs basically give it all for you. But once you have that, you can derive a snapshotting strategy on CA layers, where you just take the image strategy and pull it back by then rendering that CA layer into a UI image using this API. And then once you have that, you can derive the snapshotting strategy on views by taking the layer strategy, pulling it back, by then plucking out the layer from the UI view. And then you could, from that, derive a strategy on view controllers, where you take the view strategy, pull it back to work on UI view controllers by plucking out the view from the UI view controller. And this is why the operation is called back. It should kind of convey the idea of taking a very specific strategy and like pulling it back to a larger object, like going from image to layer to view to controller. And pretty much every view controller or every snapshotting strategy that comes with the library is a pullback of some base strategy. And so it's a very, like this idea does not exist in protocols. You have no concept of taking a conformance on of a protocol and then somehow transporting it over to a conformance for some other type. There's just like, this just doesn't exist. So that is protocol witnesses in a nutshell. I want to quickly recap how we got to where we ended up. We started by understanding that protocols are the de facto way of doing abstraction in Swift. It's highly pushed by Apple, but they have lots of problems, but they're getting better. Someday, maybe all these problems will be fixed, and we'll just be able to do more and more things in protocols. So we explored the process of how you would be able to scrap protocols and just have simple data types. And then we really started to see that they fix a lot of problems, and they unveil like a lot of interesting transformations. But I don't want to discourage people from using protocols entirely. That's not the point of the talk. It's really just to explore alternatives to protocols. So and also explore the idea of not overusing protocols, to know that there are alternatives. So the pros are pretty clear. We've talked about it, like gets around a lot of shortcomings, encourages multiple conformances, which is something we probably don't think about a lot, but is very powerful. And we can build new conformances from old ones, and they reveal lots of transformations that are completely hidden. But the cons, there's definitely cons. Swift is absolutely a protocol-oriented language, so you're going to have friction when you go against that model. And so this doesn't play super nicely with ubiquitous protocols, things that are just really kind of get their fingers in every little aspect of your application, like custom string convertible. You're not going to use this protocol witness style for that, because the whole point of custom string convertible is to have like a very simple way of plucking out a string description, like in string interpolation, stuff like that. So you're probably not going to use it. Very deep protocol hierarchies, because that turns into basically struct hierarchies where you have heavily nested struct fields. And so that's going to be kind of strange if you have a whole bunch of protocols inheriting from each other. You're going to have to dive deep into all the fields of the witness structs. And then also very advanced protocols get more and more complicated to convert. So you're not going to go and convert like the entire sequence and collection API to this style, because they use some of the, probably all the most advanced features of protocols, and it's going to become increasingly difficult to capture all that essence. So that's the end. Thanks for listening, some contact info, and thanks.